the work of Wikimedia Tunisia, as well as the Data Engineering and Semantics Research Unit from the University of Sfax, Tunisia, about combining PubMed and Wikidata to generate biomedical information. The title of the session is Let's Play with PubMed to Enrich Wikidata with Biomedical Information. I am Hussein Din Turkey, and I am a research assistant at Data Engineering and Semantics Research Unit, University of Sfax, Tunisia, and the vice chair of Wikimedia Tunisia user group. So the Data Engineering and Semantics Research Unit has been created in 2021. It is the first research structure in Tunisia specialized in Wikimedia projects. It is affiliated at the Faculty of Sciences of Sfax, University of Sfax, Tunisia. Its main objective is to develop novel applications of Wikimedia projects based on knowledge engineering, machine learning, and big data technologies. Our team is composed of major members of Wikimedia Tunisia, focusing on the technical side of the Wikimedia projects. As well, we have some primary collaborators from various institutions. For example, the Sonke Biotic, which is a community for biomedical machine learning for the African context, and Wikimedia Medicine, which is a thematic organization focusing on the medical content of the Wikimedia projects. We have as well advisors from various institutions. For example, the Institute for Technological Innovation from the University of Pretoria, South Africa, Sisonke Biotech, and Wikimedia Medicine. We are honored to announce that we have a new research project launched in this context. This work is within the framework of the project funded by the Wikimedia Research Fund to be launched in August 2022 for 1 year. This project is entitled Adapting Wikidata to Support Clinical Practice using Data Science, Semantic Web, and Machine Learning. So, as you already know, Wikidata is a structured ontological database that represents information in the form of RDF triples. This means that we have the subject, the predicate, and the object. To enrich Wikidata with semantic information in many domains, we need some tools, some computer methods and programs. And these programs will be mainly focused on some applications. For example, the research extraction, research reference identification, relation validation, and relation classification. So in this project, we are focusing on these. And for that, we are not using the full text of scholarly publications, as many do. We are probably and thinking that bibliographic metadata can be more useful in this context. For example, the bibliographic metadata have included semi-structured text providing information about research venue, papers, authors, etc. They have limited size, they are pre-processed, and they require minor use of information retrieval, machine learning techniques as well. So they are formatted and they are annotated by design. So we are not needing some advanced feature of machine learning techniques. So for PubMed, each type of bibliographic metadata is assigned a tag. For example, for abstract, we have AB, affiliation, we have AD, the mesh keywords, we have MH. And by these tags, we can extract this information without any pain. So this database can be easily used to enrich bibliographic metadata in Wikidata despite several legal concerns, but processing this data, most importantly, can be used to enrich scientific knowledge in Wikidata. For the purpose of our project, we are mainly working on the mesh keywords. So the mesh keywords, for example, are controlled keywords assigned back to PubMed records by the curators of NCBI databases. They are easier to process. They have particular layout, heading, and qualifiers. The qualifiers are predefined. We have 89 qualifiers. The headings are assigned from the medical subject heading taxonomy. So they are shortened than full text and abstracts of scholarly publications, and they reflect the output of scholarly publications and can be easily retrieved thanks to NCBI Only API, and there is even a Python library called ViewPython that can be used for such a purpose. So now we will go to screen how we do to kind of uh, use the mesh keywords for the tasks that have been defined before. So we will begin by the relation classification. So the principle of the relation classification is that we use the qualifiers of the subject and the object, as shown here in PubMed, the association of the subject and object in PubMed publications. And from that, we infer the relation type between the subject and the object of a relation. For example, we have here hepatitis C / drug therapy. So drug therapy is the qualifier of the subject, and suppository therapeutic use, so therapeutic use is the qualifier of the object. When combining these two features, we find out that hepatitis C has as a drug used for treatment suppository. So for enabling such relation classification, we need the dataset of biomedical relations. And here we can use Wikidata as a benchmark for driving biomedical relation classification and even biomedical relation extraction at a later stage. No one has think before about using Wikidata for such a purpose, but we believe that Wikidata can be used as a benchmark for training machine learning models that can be very useful for biomedical knowledge engineering. So our approach is pretty simple. So we formulated a query in Wikidata, a Sparkle query. When we extract the relations that exist in Wikidata between the subjects and the object that have mesh identifiers. So as you see here, we extracted 81,000 relations. And then we convert the subject and the object to a PubMed query, and we search the queries that have the association of the subject and the object. And then we extract the qualifiers of the subject and the object in every paper of the search results. So we are processing up to 100 publications per query. And then we are tracing a table of the association between the subject qualifiers and the object qualifiers. So like this, we obtain a matrix of mesh qualifier associations. And we also obtain an annotation of such a matrix using the Wikidata ID of the property that corresponds to the relation. So we have now a series of matrices of 89 times 89 matrices annotated by relation types that are P numbers, that are Wikidata property IDs. And these sum of matrices annotated by labels are stored in mesh to matrix dataset that we have created. So once we create this dataset, we assign the relations to superclasses. This means, for example, taxonomical superclasses. There is biomedical non-symmetric superclass. There is the non-biomedical symmetric, etc. So we are summing the relation types into kind of large families of Wikidata relations, so that we can assess the overall accuracy of our classification method using a sample kind of a sample problem sample task of classifying according to relation families to superclasses, and then to classify the relation, the matrices that we have based on 199 biomedical relation types. So once we do that, we are training our matrix to using state-of-the-art models, and then we evaluate the accuracy of and the precision of our approach using two metrics: the accuracy and the F1 measure. So as you see here, we have gone through our approach, and we have trained our approach using three models: the SVM, which is a classical machine learning model, and the deep learning models that are the convolutional neural networks mainly used for image classification, and the dense model. So as you see here, all the three models have had an acceptable accuracy rate that exceeded 60%. And for the superclass-based classification, we have an accuracy that is over 78%, which proves the promise of our approach to classify biomedical relations in the future. So our data set is available with the source code, with all the materials on GitHub, so you can access it. You can go through our source code to see how we did that, to propose better adjustment, maybe to train new models, new machine learning models that can be better than ours, and to have kind of optimizations for our work in the short run and in the long run. So another work we are envisioning to do is the use of our approach for relation extraction and validation. So we are mainly based on something called the pointwise mutual information. This metric is used to compute the association between entities. And in computational linguistics, the PMI has been used for finding collocations and association between words from corpuses. The mesh keywords are predefined and formatted, so there is no need for advanced methods for identifying associations such as word embedding, for example. So here is the formula of the pointwise mutual information. So it is a pretty simple method that is based on log of the calculation of log of the proportion of the probabilities. So when we use that, we are doing kind of search in PubMed publication to find publications about a given topic. We extract the most common mesh keywords, and then we compute the PMI between the mesh keywords to identify the most related mesh keywords. And then when we consider the related mesh keywords, we are identifying the relation type between these mesh keywords using the mesh to matrix approach that we have explained before. We have also think about using mesh to matrix for reference identification, for example. So the principle is mainly based on the mesh to matrix approach. So we are training data on mesh to matrix, and then using SHAP, which is an explainability model, we extract the features that are kind of explaining the relation the relation type, the particular relation type we are working about, for example, medical condition treated. And then we are formulating a query, a precise PubMed query, when we use the subject with the corresponding subject qualifier and the object with the corresponding object qualifier, and we formulate the query, PubMed query, and then we search and using the best match option, the relevance rank of the search results, we identify the best result that reflect the relation in PubMed, and then we adopt it as the reference of the relation. So these are our main approaches for identifying, classifying, and verifying and validating biomedical relations using Wikidata and PubMed at the same time. So now I will visualize some tools that we are using for such a purpose. So we are using the Wikibase integrator, which is a Python library that is simple to use, that is intuitive, and that can be used to extract information from Wikidata and then to add information to Wikidata. So it is pretty simple to use, and I recommend using it. The second is a tool. It is called the Wikidata Hub, and it allows to extract the IDs, the external identifiers corresponding to a Wikidata item, or to recognize the Wikidata item corresponding to an external identifier. So it is a tool forge tool. So it is sample, and it is sample to use, and it is available for anyone. The third one is the Wikidata query service. And what people do not know very much about Wikidata query service is that it can be used and it can be embedded in Python programs. So there is a code that can be copied and pasted and then slightly modified for the purpose of your knowledge-based system. Finally, there is BioPython, which is a Python library for extracting information from PubMed, and then you can use this information to process it and then get the information and then kind of add it later or inject it later into Wikidata using the Wikibase integrator Python library. So these are our references for what we do. So they are pretty our works for 2 years or 3 years for now. So I highly recommend that you see and you go through our works to learn more about what we do. As well, there are some links for the Wikibase integrator, the meshed matrix, our bots, and the Wikidata Hub, so you can go through them and to learn more about how we do the classification, how we develop our code for the relation classification and identification and the reference extraction using PubMed. And there is also a recording with more details from our presentation of these approaches at the LD4 conference on linked data. Thank you. So for now, I can get some questions from the audience, if you like. And then we can go through a demo of the source codes. Any question?
Yes, someone wants to ask a question.
Yes, can I just jump in? Are you able to hear me?
Yes, I hear you.
I have two. Thank you very much for your presentation. It's an interesting concept, but I do have a couple of questions or rather reservations. One is I find it problematic that you're using PubMed as a basis. PubMed is a cesspool. It's not curated. There are preprints that are in there. There are things from predatory journals. There are plagiarisms and retractions. And I didn't see in your list of tags that you were using for Mesh anything for these kinds of retractions or science that has been withdrawn. So that would be the issue. How would you deal with this kind of thing? The second issue would be the problem of conflicting research. For example, you will find lots of papers in PubMed that say for COVID, the medical condition is treated with hydroxychloroquine. And then you'll find papers that say, no, we do not treat COVID with hydroxychloroquine. And so you would have to decide which of these is more likely to be correct. And so that would pose a problem. And because of these two issues, I think it would probably be good if you didn't put things back into Wikidata, but had your own Wikibase implementation that you could use with linked open data to make some sort of a federated kind of query that you could use Wikidata and your information, but to keep it separate from Wikidata. So I'd like to hear your take on these issues. Thank you.
Yeah, concerning the extraction, I was about to go through the source code. We have gone through several tricks for doing that. In fact, PubMed has a tag for partially retracted and retracted articles. So we can use this tag to eliminate the retracted output. So that's pretty simple, and we have done that in our code, and we can show you later how we did that.
Okay, I just put this into the chat, but they don't have them all marked. That's part of the issue. PubMed, as I say, is a disaster, and so there are many that are retracted that aren't actually marked in. So you would have to go to the individual publishers, and that would be a lot of work trying to decide if something is correct or not.
Yeah, the second thing that we are envisioning to do is to do like the reference island tool. So we are obtaining the data set and then injecting it as the source of Wikidata gain, and then let the user approve or not approve a new relation or a reference to a relation, etc. So that's the second thing we are working about, and we got funding just to do that, in fact. Any other question?
Then I would jump in and continue. There's not just one person to say something is true or not. You'll have people who are violently of the opinion A is true, and there are other people who are violently of the opinion that not A is true. And so this is something that has been solved within Wikidata, that there are multiple truths that are possible. How will you be doing these multiple truths then in your medical information?
Yeah, we have conflicting information in medicine in general, and so we cannot eliminate all of them. These are two perspectives for solving the same problem. So we need to respect each side of the information provided. So we are providing each information, and we say that there are some people that are saying this, and there are some people that are saying that. And then there are some kind of scores-like properties to like of classify the relations according to their rate of confidence related to that. So if you are confident about a given relation, you can assign a reification when you say that this is sure, or this is probable, or this is not probable. And this has been applied for COVID-19, for example. You can see for COVID-19 that there are some rates, of confidence for some statements. So you can use that for the properties as well. So that's how we deal with that information.
That would be cool to show. Please show us that.
Yeah, sure. Yeah, so maybe you can go to COVID-19 because we have published a paper about COVID-19 as well. So we see how we model that. Okay. So we have properties here. Okay. For example, we can go to symptoms, for example, and you see here nature of statements here. You see that? So the nature of statements can show you the frequency of the event, or if the event is sure or unsure, etc. So there are few kinds of properties that are used as a reification to the main relation, and that can be used to identify our certainty of about a given statement. For example, this. You see that? So this is an hypothesis. It has not been proved through clinical trial. So it is marked as an hypothesis. So that's how we do that. I can show you as well. You see this, for example, is the source and circumstances. So it is an estimate. So it is not proven through an epidemiological study. So you see, we have indicated that the source and circumstances are estimates in this context. So I can show you as well how we did what we did about retracted papers as well. So this is our code from what we have developed. So you see there is okay. There is these conditions, these two conditions here, RIN and PRIN. And these two conditions means that we are verifying whether the research paper has been retracted or not. And this is for the full retraction of the research paper, and this is for the partial retraction of the research paper. And we are considering these two namespaces. So if the paper is marked as retracted or partially retracted in PubMed, we are not considering that.
We are slowly running out of time, and I see two more questions in the sidebar. One is by Hogu. How good is, from your point of view, the medical data in Wikidata? So how well are diseases classified?
Yeah, we need a lot of work, and that's why we need automation. The purpose of this project is that the medical knowledge is huge, and we have 40 million of articles in PubMed. So we cannot model all the data using users. Even if we have a community of medical practitioners and medical students that is active and is created every day. And there is also a change of the nomenclature, which means that the name of a drug or of a disease or of a sign can change from a time to another due to several circumstances. So we cannot do that. And that's why automation can be useful to help. I don't mean that it will replace the users, the Wikidata users, in their role of editing Wikidata, adding new information to Wikidata, but it will help. It can be just a validation task instead of a creation task from scratch.
Thanks. And one last question we have in the sidebar by IMT. Can we use data sets of the World Health Organization or any health orgs?
Yes, the answer is yes. But there is one condition. The first two conditions, in fact. The first is the technical constraints. We need to verify that the license of the dataset goes well with the CC0 license of Wikidata. The second one, that the information needs to be structured, because if it is not structured, you need to kind of convert it into tabular data, and this will take time and efforts. I think we ran out of time. Yes.
Thank you.